Hello everyone, and welcome back to my repair channel. Today I'm putting up a super breakout repair. It had a few interesting faults, so you might find interesting. So without further ado, let's head over to the bench and start looking at this super breakout board from Atari 1978. Alright, this is super breakout board number 2 of this job that I'm doing. And yeah, I've got it turned on right now. I just got it out of the bag and put it on the board bench and turned it on, hooked it up, turned it on, and it's a bunch of garbage. Garbagey garbage on the screen. We got a big ugly socket right here. And I mess with it and I get different garbage. That definitely has to be replaced. And then we can start from there. This socket right here, I don't have much love for. We have bipolars. We have a mix of bipolar ROMs and regular ROM. So these two, the program that are held in these two ROMs here are actually over here in these chips. So kind of a mix. Whatever Atari had on hand is what they used for this one. Okay, so first things first is I want to check the voltage and see if we need to replace this guy and then replace this socket. So I'm going to go ahead and measure the voltage. Let's see what we got. Okay, I'll see if I can't do this one-handed. Get the measurement on the voltage. And you can see it is outputting 4.96, which is perfectly good. So we do not need to replace this regulator, which is a good thing. So next thing is just go ahead and replace this socket. And I'm going to go ahead and replace this socket as well. And I have seen problems with these sockets as well over here with these ROMs. These things get so hot. And they need an absolute good connection to these sockets. So probably going to end up replacing these, this, and go from there. I think I'll hold off on replacing these because these are less apt to be bad than these. These wider sockets are always the ones that are problems, but I have had problems with these things in the past as well. Just because they run so hot that the connection just fails. So this one looks like it was actually kind of replaced at some point. Yeah, so anywho, let's get down to it. Okay, so socket replaced, put back together, and we now have, this is our garbage. This is our stable garbage, if you can say stable garbage. This needs to be twisted slightly, like that. That's better. Yeah, but that's the trash. So the next thing I want to do is put the fluke on this thing and read ROMs and RAMs and find out how many of these RAMs are bad. Because I have a sense, I have a feeling that some of these 2102 RAMs are no good. Okay, so I put the fluke on it and the fluke wouldn't do anything. It was just giving me a pod timeout error. And I checked the fluke, you know, I plugged it into itself and it said that the fluke was okay. So obviously the problem is in the CPU circuitry. It's not even allowing the fluke to work. So I got the little scope out and I'm going to be probing around on the board. I'll set this camera up and focus it on the little scope there so that you can see what I'm looking at, and you'll have the overhead view of me probing the board. So we'll do it together and see if we can find out what's actually going on with this thing. Okay, 6502 and pin 4. Let's check the reset line. That's 40, and it's resetting. Pin 4, I believe, is one of the interrupts, so it looks like it's constantly interrupted. Let me get my 6502 sheet out so that I can actually see what is the actual pin out of the 6502. I think that pin 4 yes, pin 4 is the IRQ. And it is always in an interrupted state. So that tells me the CPU isn't even going to attempt to do anything. So I want to get the schematic out. We'll get that next. Okay. This is the schematic for Super Breakout, and we'll open up to the CPU section. We've got the whole manual printed out. Okay, this is the sync, and here's the CPU. Here's the CPU portion of the schematic. Pin 6 is non-maskable interrupt. And that's right here. And that's high, which I would expect that. Our problem is the IRQ. Pin 4 is always low. That's why my fluke wouldn't do anything. Let's look at this 74 over at M9. That is... M9 is way up here. M9 is right there, I believe. No, it's right here, I think. Yeah. M9 is way up here. And we're going to look at the high side of M9. Here is pin 13, which is the reset, which is pulled high. Interrupt acknowledge is pin 10, and it's high. It does go low every now and again. That looks proper. Data on 12 is grounded. And then 16V is our clocking signal. That's right there. And here's our... We're getting no count out of this at all. And we should be getting a count. That's 74. So, and the output is pegged low all the time, so this may not work jumping the chip over, but we'll be able to see it kind of fighting against each other. Maybe. No, we can't either. This is the clock. Data is low. And our set signal, single shot. I thought I saw it going low. That's interrupt acknowledge. So maybe it's not going low. This is interrupt acknowledge. If this does not go low, then this thing will not count, because data is low and our clock is continuously clocking at low. I thought that this was going low. I thought I saw this go low. This is pin 10. This is the interrupt acknowledge, and it doesn't look like it's going low. I can put it on a single shot and it's not capturing anything. I thought I saw this go low, but maybe it was errant or something. So this signal is not going low, interrupt acknowledge, and if this doesn't go low, like I said, it will not preset the IRQ. So it looks like we have to go back and find out the interrupt acknowledge signal. That looks like our problem. So it's not the 74. So let's find in the decoding where that signal comes from. Interrupt acknowledge. And it's right here. I turn the page and it's a 9301, which is a 42. And that is E8, which is right here. Here's the inputs to this. That one's high all the time. That is address. Now this 9301 is a different pinout. It's the same functionality as a 42, but it's a different pinout. So yeah, pin 15 is the least significant input, then 14, then 1. And then the most significant input is pin 2. And it's high all the time. Which means it'll only be 8, 9, or 10. Or 8 or 9. Going low. Which would be pin 12, or no, pin 1, pin 12, 12, which is right here. That's timer reset, and it's not going low. Or 13. Are any of the okay, what are any of these? 9, 8, 7, 6, 5, 4, 3, 2, 1. 7, 6, 5, 4, 3. 7, 6, 5. 4, 3, 9. This is the interrupt acknowledge signal, and it's a software driven signal. Seems like the fluke would have still worked. I'll put a 9301 on it. This is 9301. I don't think the 9301 is bad though. Could be. Can't see what I'm doing. This is that interrupt acknowledge signal, and I don't see it going low. Actually, I did see it go low. Perhaps. I did. See that? That's a clear low. Okay, let's see if it does that on its own. Okay. I'm going to have to analyze this chip. I think I'm going to have to get the analyzer out on this, because I have to verify, because that's the interrupt acknowledge signal that comes over to the CPU, or comes over to the 74 and sends the interrupt, the IRQ signal high, so that the CPU can actually work. So if it's not doing that, it's not going to work at all. So yeah, 9301s. I'm going to go ahead and turn it on. Let's look at some of these other 9301s. And that one is strictly getting its inputs from the address. So it's software driven. Except for the upper bit, which is off of P3. P3 is a 32. P3 is a 32. Nothing there. A high. That's got signals. I need to change this. Let's do that. Okay. That's working. I see a signal there. Okay, that's good. D2 is another one of those 9301s. You know what I want to do? Let's do this. Let's pull that pin up. Yeah, look at that. That's pin 9. That's interrupt acknowledge. And it is clearly very busy. And down at the chip, it's not. Well, I did see it's going low. I see it going low. Yeah, it is going low. That's pin 10. And I see it, It is. Yeah. So is this chip, is this going high? It is going high. So that is working. Oops. Yeah, I see this going high. See that? Yeah. That's this pin. It's this right here. Yeah, it's definitely working. So that was just a whole mess of nothing. Yeah, it didn't look like it was working before. Now it is. So who knows? That's not the problem. Why would my... How come this is low all the time? If this is that signal, why is it low all the time? Pin 4. I think this is a software issue. I really do. Why did my fluke not work? Why did my fluke not work? Alright, I'm going to have to investigate. Okay, so I found out why my fluke wouldn't work, and the main culprit on this board. I just started probing around on the signals to the CPU, and I came across pin 37, which is the CPU's clock, and it looks like that. So looking at the schematic that comes off of J8, the 32 at J8, and if I look at the 32 at J8, it's right here. We have input, input, bad output, input, input, another bad output. This whole chip is bad. In, bad out, and input, which this is probably from the same chip, bad output. I would imagine that this input on pin 4 is probably that signal right there. No, it's not that signal. It's that signal. It's on the same chip. So it looks like pin 11 just wraps around and goes to pin 4. Yeah. So that chip is no good. And yeah. You have a 174 at A7. That's this guy right here. There's your clock. And we'll just look at this. I see a signal there. That looks okay. That looks good. 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 Yeah, that chip looks fine. It's just this 32. Okay, I've removed and replaced that 32. Now you can see I've got one of the legs lifted because this is what that signal is supposed to be like on that leg, that pin 6. But down on the board it is held low. If I get on it. Yeah, it's held low. You can see that. Now, this is not my greatest socket job. This socket did not want to go on the board, and I was just kind of lazy, and I soldered it the way it was. And I need to see and make sure that this ground didn't leak over and short to that pin. So I'll do that really quick, and if it isn't shorted, then whatever's holding that line is holding it low. And I'll have to get the schematic out and find that very pin and see what it's connected to. Yeah, there was just a little bridge right there. Sloppy work. Shame on me. Okay, so that did fix that. No longer grounded. So our signals are all looking good off of this chip. And we are still not working. But the garbage is a little bit better. Now I should be able to put the fluke on this thing. Because now we have a sensible looking clocking signal. That's our CPU clock. And we have our interrupt looks good. Our non-maskable is high, which is good. So now it's just a matter of putting the fluke on this thing and finding out what it tells us. And I think it's going to tell us all that we would need to know. I think we got RAM issues. I think we might even have ROM issues. So fluke is next. Okay, I got the fluke out. ROMs checked perfect, as they should. RAMs, I get a decoding error, and I've gotten bit 5, I've gotten bit 4. Let's try to do let's do a RAM at 0 to 7F. And that'll give me bit 5. I've had, oh no, it's bit 5. It's at address 40, bit 5. So it seems to always be bit 5. Let's just go random at something random. That was okay. RAM short. Bit 5. Okay. Bit 7. So we got some kind of weird, I mean, this is kind of almost, this is looking like it could be a bad chip throwing off all of the decoding, which is going to be hard to find. That was okay. Alright, so 4FF was okay. Okay. 5 to 5FF is not going to be okay. Bit 7. This one gives me bit 7. Okay. This one's probably going to be bit 5. Nope, that one passes. And RAM short at bit 7. Okay, at 765 bit 7. So I need to write this out and actually try to find out what's going on here. Okay, so I kind of wrote this out, and this is our address space. Remember, 4 whatever was okay. So 4, these don't matter. This is 4, and then these don't matter. That was okay. 5 range, right here, 5, gave me bit 7 decoding. 6 was okay. And 7 gave me a decoding. The thing that I see in common here, which could be our issue, is this bit right here. When it's supposed to be 1, maybe it's stuck low. Let's try writing into 400 and then see if we read the same thing back at 500. So let's do that. Let's write at 499. Okay, now let's read at 400. We get 99. So that's what's going on. It looks like we have a stuck bit. And so also we can read at, what was it, 700? 400 and 500. And then if I write at 6, now I'll write at 600 AA, and that'll probably show up at 700. It didn't. FC. Let's write at 700. Oh, I don't know. EE. Okay. Oh. So let's try reading at 600. AA still. Okay, that's kind of strange. If we write at 400, I would expect this to be universal. We write at 400, that's right here, the top line. And we're going to write let's write DD, double D. Everyone's favorite letter, double D. Now if we read at 500, if this bit right here is stuck low, then we should get that double D at 500. So we'll read at 500, and we don't get it. Okay. Bit 7 decoding. So let's write at 4. Let's go 400, let's say. Let's try it again. Let's do a write at 400, and we will write DD. Okay. Now, maybe it is bit 7, and let's read at 480. 4800, and maybe that DD will be there. Read at 4800, and it's not. 400 and 48, so bit 7 wasn't an issue. This is strange. Right at 400. Remember I did 99? And then I read at 500 and 99 was there. And it won't run. It's like it cleared itself up. Now it's not working. Now it's bit 9. 546. Bit 9. So it's like we have, there's 546 again, bit 9. Now it's giving me bit 9. Same thing. So now maybe let's read at 400. FD, let's write at 400. DD. And bit 9 is this one, so let's read at 600. 06. It's just completely random, which kind of tells me that one of these or two of these RAMs is bad and messing up the whole decoding. I don't think it's hardware decoding because it's too random. So I really think this is a situation where these RAMs just have to come out of the board, unfortunately. Because 1, 2, or 3 of them are just mucking up the whole system and throwing random decoding errors. That's what I think is going on. So that's the way I'm going to approach it. I'm just going to remove all these RAMs. Well, I thought to put this thing into test. So I did put it into test. And okay, so the manual says a high tone is a bad bit. So it's telling me that data bit 2, 0, 1, 2, it's telling me that data bit 2 is no good. So that is 0, 1, 2, data bus 2, data bit 2. That's this guy right here, J4. So let's pull J4. That's 0, 1, 2, 3, 4. That's this guy right here. That's what it's telling me is bad, is this guy. Okay, so let's pull that one. Okay. It's good to go. Let's see if the pot works, and it does not. I'm turning the pot right now. These values should be changing and they're not. So, well, we're getting closer. Let's take it out of test. There we go. It looks, the ball does not look good. So we have problems with the ball all three of them, and the pot don't work. But our playfield looks good. So we'll hunt down the ball issue. We got our RAMs, our program is running good. So yeah, I know these 165s are in the ball circuitry, turning it on. I don't think those are a problem because it's on. Could be. But all three, it's going to be something universal to all three of the balls. Probably, oh, I don't know. I have to look at the schematic and find out what is universal between all three of these balls. Does it have the same addressing? Do they have the same addressing? I don't know if they do or not. Let's try to find some of that stuff, shall we? Playfield. See, here's our ball turn-ons. Okay, inhibit, which means probably no shifting. We have a clock. We have a 6 megahertz clock. I'm sure that's fine, right? We have these 163 counters. Ooh, counters. So this is the, we're going to want to focus on this. First thing let's do is get the ball circuitry correct. Then we'll move on to why does the pot not work. First things first, I'm going to start right here. Okay, so we're going to work on the ball circuit, and we're going to just look through it and make sure that they look the way that they're supposed to, and then we'll move on to why does our pot not work. So we got to this part of the schematic, and I just want to probe around these 165s and these counters. I'm going to start with these counters. I think that's what we said we would do. So we'll start with R5 and R6. 0, 1, 2, 3, 4, 5, and 6. These two counters. And we'll just look at everything and make sure. Starting with R5. Okay. And moving to R6. So far it looks okay. Now let's try P5 and P6. Nothing alarming there. And then N5 and N6. Okay, so that all looks okay. So now let's check out these 20s, L8, L8, and L6. L8, 0, 1, 2, 3, 4, 5, 6, 7, 8. So L8. Okay. And L6. Okay, that looks fine. And then let's look at the outputs. Let's look at the inputs, actually, the control inputs to the 165s. So the address is 11, 12, and 13. These are the three 165s right here. So 11, 12, and 13. 11, 12. 12 is low all the time. That's concerning. And that would make sense. It's an address. It's going to be because all of the balls have the same failure. They have the same look, if you remember. And let me put this to, let me try. That's progressive. Yeah. I'll just move the camera over here and you'll see, we'll get a refresher. All of the ball, they look like that. All three of them have the same look. So it's going to be something universal, and it's probably that address bit. It's probably stuck low. So, and because all three of them were like that, it tells me that it's something, it's just something universal between all three of those. So it's probably that bit. That address bit's probably stuck low. And that's video bit 6, vid 6 on pin 12. 11, 12, 13. No, wait, it's pin 14 that's low, and that's supposed. Okay, false alarm. 11, 12, 13 all look okay. Let's try pin 1, which is, it's just a shift signal. That looks good. How about clock on pin 2? That's good. What about our outputs on pins 7? Yeah. Okay. Alright, so actually those look good. So, very strange. They look good, but they might not be good. So we need to actually find out those address bits. I'm still concerned about the three address bits that are addressing these 165s. So I'm going to go back and find those video signals, vid 5, 6, and 7, and I want to look at that closer. It's got to be from the RAMs, right? Alright, vid 5, 6, and 7 are from a bipolar ROM. So let's look at that at K6. Zero, 1, 2, 3, 4, 5, 6. This guy right here. Let's look at the addresses to this on 10, 11, 12, 13, 14. 10, 11, 12, 13. Addresses look good. Okay, let's back up one step, because this I'm going to highly doubt is bad. I'm not suspecting this bipolar ROM to be bad at all. It's going to be the addressing to it, I believe. So let's look at the 174 at L5, which is right here. Would actually be good to analyze this. Because it looks fine. But that does not mean that it is fine. There's also another address bit, display 7, and there's also, oh, there's an 83. There's two 83s that are involved in the addressing to this. That is probably what the problem is an 83. But we'll just continue. M9 is a 74 that provides an address bit. That is, M9 is way up here, and we're looking at the low side of that chip, M9. No reset. There's your data. There's the clock. That looks okay. Alright, let's get to these 283s. There's one at C4, one at L4. Right here. There's only one way to really truly tell if these are good or not, and that is to analyze them. Well, we're on the right path. We're on the right track here. Okay, so we're on there now. One, 14, 15, 16, 17. So 16, 17. 13 and 5 is 18. Alright. Okay, so far so good. One, 5, and 11 is 17. 0, 5, and 10, 15. So this one seems to be fine. So no smoking gun yet. 1 and 10 is 11, and 4 is 15. 0, 10, and 0 is 10. 1, 10, and 13 is 14 or 24. So this one seems to be fine. I don't see any no problems with this one. So let's get on to the other one and see how it looks. Okay, I'm on the other one. Alright, why do I got a trigger on? Okay, 1 and 15 is not 12. 1 and 0 is 1. 14 and 8 is not 18. 14 and 9 is not 19. So here, this looks like the problem. 8 and 5 is 13, not 9. 8 and 5, yeah. Let me make sure I'm on it good. Let me just make sure I'm on it properly. But it looks like this is the problem. Alright, I've readjusted the thing. Let's see. Yeah, 0, 5, and 0, it's got 1. 0 and 11 and 11 is 22. And 0 and 11 and 0 is 11. That's good. 14 and 4 is not 2. 14 and 1 is not 11. So yeah, this is definitely the problem, is this chip right here. And jumping it did not fix it. So I mean, and we don't have any smoking gun as far as just stuck bits. But let's try to understand what's going on here. I want to get my pad and paper. If I can find it. Now I want to write down some of what we're seeing. Okay, so we're seeing 14 plus 4 equaling 2. We're seeing 14 and 1 equaling 11. We're seeing 13 and 3 equaling 13. Actually, we're seeing 14 and 5 equaling 3. 14 plus 5 equaling 3. That should be enough. So let me shut this off and we will take a look, see if we can figure out what is actually happening here. Okay, so here I wrote out what we are seeing. And we are seeing 14 plus 2 equals 2. 14 plus 1 equals 11. And we're seeing 14 plus 5 equaling 3. Well, here's 14 plus 5. 14 is right here. 5 is right here, binary. And then you add them, you get 1, 1, 0, and carry the 1. And so you get that, which is, this is 19. But if you drop this low, if you just make this a 0 instead of a 1, you have 3. And that's what we're seeing is 14 plus 5 equaling 3. So the carry bit is always 0. That's the problem. And on this one here, well, that's one I just did, 14 and 5. Here's 14 plus 4, and we have 14 and 4 equaling 2. And the same thing, here's 14, here's 4, and then you add those, 0, 1, 0, carry the 1, and then 1, 0, which is 16, 17, 18. 14 plus 4 is 18, but if you drop this to a 0, then you have 2, which is what we're seeing. We're seeing 14 plus 4 equaling 2 on the analyzer. So that's what the problem is. The carry bit is stuck low. So we'll go ahead and fire this thing back up. Oh, it's already fired up. So pin This one right here, the carry bit is pin 14. And it's not always low. So was I just not on it correctly? I'm going to get back on it with the analyzer one more time and find out, because we're getting it like this, but maybe I wasn't on it good enough. I'm going to try it again. Okay, yeah, that bit, the carry forward bit on that chip is not stuck low because we have 17 right here. And that would indicate that that carry forward bit is a 1 because we're over 16, and 4 bits in binary is 15, so that fifth bit going high is going to put you over 16. So yeah, we have it there, but if you see, this says 13 and 4. It's counting late, maybe. Here's 12 and 15. That actually is correct, 27. 12 and 0 right here, it's got 8. Yeah, this chip is just not right. It's not stuck low or stuck high or anything like that. It just doesn't count right, so this is the problem. Okay, 83 replaced. And our 3 ping pong balls are tennis balls, whatever you want to call them. They look like they should now. So that fixed that. Now we need to move on to our paddle. Does not work. We can go ahead and start a game. Let's go coin. Start. I should be able to move around with my pot, and I can't. It don't move at all. See it down there in the corner? Don't move at all. But the inputs seem to work, so let's go ahead and serve. Sounds good. I think it'll serve on its own, right? Well, maybe not. Let me hit the serve button again. A little shaky here. There. Yeah. So it seems to sound okay. We don't know if the bricks are breaking properly. We got to fix the pot. So, pot, why don't you work? Pot. Let me find the pot circuitry. Yeah, let me find that and then we'll come back. Okay, here is the pot circuitry. Pots come in off the edge connector right there, and then they go into this comparator. LM319, I believe, is a comparator. And then the outputs of that go to a 132, which is a Schottky NAND gate. So the inputs are pins 10 and 12. So we should see movement on 10 and 12 when we turn the pot. So let's zoom in. I'll zoom you in here. Okay. Try to get this thing situated for you. Okay, now when I get to pins 10 and 12 of this, and that's this chip right up here. here's pin. Right here's pin 12. And I'll move the pot, and I get nothing. And if I move it to 10, 8, 9, 10, here's pin 10, and move it around, I get nothing. So I'm suspecting that the LM319, that comparator, I'm suspecting that that is no good because I'm not getting any kind of output out of it into those pins of that 132. So I'm going to go ahead and remove and replace that LM319 and go from there. Okay, I replaced the 319, this chip right here in the schematic. And it works. So that is that. So I'm going to go ahead and set up and play some of this, make sure it operates the way that it should and all of that. Okay, serve. I gotta hit start, I guess, and serve, and I gotta try to hit the ball. Counts right. Darn it, I had it going pretty good there. Oh, I got this one on 5 balls. Last one. Last try. Darn it. Well, I was trying to get it up into that top, but I couldn't quite make it. So, I mean, I think we have ourselves a winner. Cool game. Hard game. Okay. So we tested the voltage, verified that the voltage is fine. This is a good regulator. We have replaced the sockets, these two. I replaced one RAM. I replaced a 83, and I replaced a 319. And I replaced this chip, which is a .32. So that's it. That's all you need to do to get your Super Breakout back up and running. So as always, I will go ahead and let this one run for a little bit. A few hours anyway. We'll see you all on the next Classic Arcade Repair. Thanks for watching. And a big shout out to all the channel supporters and Patreon supporters. Appreciate each and every one of you. Thank you for watching, and we'll see you on the next one.